On the first day of July 2025, a telescope in the Chilean Andes captured something extraordinary. The ATLAS survey system, designed to scan the heavens for threats to our planet, detected a moving point of light against the star field. Within hours, astronomers around the world turned their instruments toward this newcomer. What they found would shatter every comfortable assumption about comets, about interstellar visitors, and perhaps about our place in the cosmos itself. The object received the designation 3I Atlas. The I stands for Interstellar. It is only the third confirmed visitor from beyond our solar system ever detected. But unlike its predecessors, this object would not slip quietly through our neighborhood and disappear back into the void. Instead, it would trigger an unprecedented response that reverberates through the halls of NASA, the European Space Agency, and the United Nations itself. In September 2025, the International Asteroid Warning Network made an announcement that sent ripples of unease through the scientific community and far beyond. They activated a planetary defense protocol specifically for 3I Atlas. This is the first time in human history that such a measure has been taken for an object that is not on a collision course with Earth. Think about that for a moment. Our planet's defense systems, designed to protect us from asteroid impacts, have been engaged for something that will never strike our world. The official explanation speaks of unexpected variations in brightness and trajectory. But those words, clinical and measured, mask something far more profound. What could possibly justify such an extraordinary step? The protocol is not a simple observation campaign. It is a structured training exercise, a mobilization of resources across multiple space agencies, running from November 2025 through January 2026. The stated purpose is to learn how to track an unpredictable object. But unpredictable in what way? Asteroids follow the laws of physics. Comets follow the laws of physics. What makes 3I Atlas so different that it requires the activation of planetary defense systems designed for existential threats? The answer lies in a cascade of anomalies so profound that they challenge the very foundations of cometary science. Thank you for being with us. Please subscribe and leave a like. The first anomaly appeared almost immediately. As telescopes captured early images of 3I Atlas, they revealed something that should not exist. The object displayed an anti-tail. In the physics of comets, solar radiation and the solar wind push material away from the sun, creating the familiar tail that streams behind these wanderers. But 3I Atlas was different. Its tail pointed toward the Sunday. Imagine watching a river flow uphill. Imagine watching smoke descend instead of rise. That is the level of wrongness that astronomers witnessed. The anti-tail defied the fundamental mechanics that have governed cometary behavior since we first understood what comets are. Professor Avi Loeb of Harvard University, a theoretical astrophysicist known for his willingness to explore unconventional ideas, immediately recognized the significance. He suggested that what observers were witnessing might not be a natural phenomenon at all. He proposed that the anti-tail could represent a braking thrust, the signature of a craft performing a deceleration maneuver as it approached our Sunday. Then, as if on cue, the anti-tail disappeared and a conventional tail formed. Direct source attribution. The shift from an anti-tail to a conventional tail could represent a transition from a braking thrust to normal solar wind dynamics. Loeb stated in his analysis of the early observational data, the object had seemingly switched modes. It had displayed one type of behavior, impossible by natural standards, and then adopted another. The question that haunts every analysis is simple and terrible. Did something change its configuration? But the anti-tail was only the beginning. As more sophisticated instruments turned toward 3I Atlas, They began to detect its chemical composition. What they found was impossible. Comets are ancient relics, frozen time capsules from the formation of star systems. They contain water, ice, dust, and various compounds, but they follow predictable chemical ratios. These ratios are not arbitrary. They reflect the fundamental processes of stellar nucleosynthesis, the forging of elements in the hearts of stars. When a comet from our own solar system releases gas as it approaches the Sun, we can predict what that gas will contain. Iron and nickel, both metals formed in supernova explosions, appear together in specific proportions. 3. IATLAS breaks this rule completely. Spectrographic analysis revealed nickel vapor pouring from the object. But there was no corresponding iron signature. The nickel-to-iron ratio was more than 10 times higher than any known comet. Some scientists, including Loeb, have described this as a metal alloy composition never observed in nature. Let that sink in for a moment. We are looking at a chemical signature that does not match any natural object ever studied. Not comets from our solar system, not comets from other star systems, not asteroids, not any known class of celestial body. The rules that have governed cometary chemistry for decades simply do not apply to 3 IATLAS. One science broadcaster, analyzing the spectroscopic data, made a statement that captures the profound unease rippling through the astronomical community. Direct source attribution. The gas pouring from 3I Atlas is not just rare, it is unique. The rules that have governed comet science for decades fall apart in the face of this data. Imagine being a scientist who has spent a career building an understanding of how comets work, only to encounter something that renders that understanding obsolete. Imagine the instruments returning data so anomalous that you check and recheck your equipment, certain there must be an error, only to find that the readings are correct. The error is not in the instruments. The error is in our assumptions about what is possible. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, added another layer to the mystery. Its infrared spectrographs penetrated the coma surrounding 3I Atlas, the cloud of gas and dust that envelops the nucleus. What Webb revealed was a composition profile unlike anything in our catalogs. The coma is extraordinarily rich in carbon dioxide and remarkably low in water. Every comet we have ever studied closely, every visitor from the outer reaches of our solar system, shows a different balance. Water ice is the primary volatile. Carbon dioxide is present, but not dominant. 3. IATLAS inverts this relationship. It is as if the object formed in a completely different type of environment under different chemical conditions, following different rules of accretion and composition. The European Space Agency found themselves in possession of an unexpected opportunity. 2 of their spacecraft, Hera and Europa Clipper, were positioned along trajectories that would take them through the tail of 3I Atlas between late October and early November 2025. These were not missions designed to study interstellar objects. They were en route to other destinations. But the universe had arranged a cosmic coincidence, and ESA's mission planners moved quickly to capitalize on it. Colin Frank Wilson, an ESA project scientist, confirmed that their Mars orbiters had already conducted observations during a close pass on October 3, 2025. The data from that flyby, combined with the upcoming tail intercepts, would provide unprecedented in-situ measurements. For the first time, instruments could sample directly the material streaming from an interstellar visitor, analyzing its composition with a precision impossible from Earth-based observation. But as those spacecraft prepared for their encounters, 3I Atlas was moving into a phase that would render it invisible to human eyes. The object entered solar conjunction in mid-October. This is the astronomical term for when an object passes behind the Sun from Earth's perspective. The overwhelming glare of our star blocks any view of what lies beyond it. For 6 weeks, 3I Atlas would be hidden, passing through the region of space closest to the Sun, unreachable by our telescopes, unobservable by our instruments. It will reach perihelion around October 29, 2025. This is the point of closest approach to the Sun, the moment when solar heating is at its maximum, when any volatile materials in the nucleus are vaporizing at their highest rate. It is also the most energetically advantageous point for any course change. The physics of orbital mechanics dictate a principle known as the Oberth effect, a spacecraft that fires its engines while moving at high speed near a massive body like the Sun can achieve far greater changes in velocity than the same burn performed in deep space. It is a multiplier effect, leveraging gravitational potential energy to amplify thrust. Every mission planner knows this. Every spacecraft sent to the outer solar system has used this principle. Avi Loeb has been explicit about what this means for 3I Atlas. If the object were to perform a powered maneuver at perihelion, it would emerge from behind the Sun in early December with a velocity or trajectory that cannot be explained by gravitational forces alone. The difference would be measurable. The change would be undeniable. And it would be proof. The scientific establishment has not been idle in the face of these extraordinary claims. Dr. Perez Couto and his team at the University of A Coruña in Spain have run extensive simulations of 3I Atlas under various natural scenarios. Their models explore whether unusual outgassing patterns, asymmetric jets of vapor from the nucleus, or other known cometary behaviors could explain the observed anomalies. Their conclusion thus far is that no evidence of artificial interference is required to explain the data. This is the heart of the scientific debate. On one side stands the principle of parsimony, the idea that we should not invoke extraordinary explanations when ordinary ones suffice. Comets are strange. They behave in unexpected ways. Perhaps 3I Atlas is simply a very unusual comet from a very unusual stellar environment. Perhaps its chemical composition reflects formation conditions we have never encountered. Perhaps its trajectory, its anti-tail, its metal-rich emissions are all natural phenomena we simply do not yet understand. On the other side stands the accumulation of anomalies. At what point does a series of individual improbabilities combine to suggest something fundamentally different? At what point does the natural explanation require so many caveats, so many special conditions, that an alternative hypothesis becomes more economical? But there is another dimension to this story, one that adds a layer of tension beyond the scientific debate. Avi Loeb has publicly accused NASA of a lack of transparency. He has pointed out that the Mars Reconnaissance Orbiter, one of the most sophisticated imaging platforms in orbit around another planet, was positioned to capture close-up images of 3I Atlas during the October 3rd flyby. Those images, if they exist, have not been publicly released. Loeb has contrasted what he perceives as NASA's reluctance to share data with the European Space Agency's more open approach. He has suggested that information is being withheld, that data showing something unexpected or controversial is being slow-walked through internal review processes, while the scientific community and the public remain in the dark. Is there a cover-up? Are there images sitting in classified databases that show something so extraordinary that disclosure requires careful management? Or is this simply the normal, frustratingly slow process of scientific data validation and peer review, amplified by the extraordinary public interest in this object? The truth is that we are living through a moment of profound uncertainty, An object from another star system is passing through our cosmic neighborhood, displaying behaviors that challenge our understanding. Our space agencies have activated defense protocols never before used for a non-threatening object. Scientists are divided on interpretations. Data is flowing in from multiple sources, but the picture remains incomplete. And 3I. Atlas itself remains hidden behind the sun, approaching the point of closest passage, where any secrets it might hold will be revealed or concealed based on actions we cannot observe. In early December, it will emerge. Telescopes around the world will lock onto its position. Spectrographs will analyze its light. Trajectory calculations will be updated with the latest positional data. And we will know. We will know if it has changed course in a way that cannot be explained. We will know if its velocity has shifted beyond what gravitational interactions can account for. We will know if the metal emissions continue to defy natural chemistry. We will know if the object maintains a trajectory too perfect, too aligned with the ecliptic plane, to be a random visitor from interstellar space. The statistical improbability of that trajectory deserves its own examination. The ecliptic plane is the flat disk in which our planets orbit. It represents less than 1 degree of the full sphere of space surrounding the Sunday. For an object entering our solar system from a random direction in interstellar space to arrive on a path so closely aligned with this plane is extraordinarily unlikely. It is not impossible. Unlikely events happen. But it adds one more entry to the growing list of coincidences and anomalies that surround 3I Atlas. Some scientists have suggested that perhaps interstellar comets naturally align with galactic planes, following streams of material between star systems. Perhaps there are preferred pathways through interstellar space that we are only now beginning to detect. Perhaps the alignment is meaningful, but not artificial. These are reasonable hypotheses. They deserve serious consideration, but they remain hypotheses, untested theories proposed to explain an uncomfortable observation. What makes this moment in history so extraordinary is not just the object itself. It is our response to it. Humanity has built a network of telescopes, spacecraft, and early warning systems. We have developed the technology to detect and track objects millions of miles away. We have created international protocols for responding to threats from space. And now, for the first time, we have activated those protocols not for a rock that might hit us, but for something we do not understand. The International Asteroid Warning Network is coordinated by NASA, but operates under the endorsement of the United Nations. It represents a global commitment to planetary defense, a recognition that threats from space transcend national boundaries. The activation of this network for 3I Atlas is a statement. It says that uncertainty itself can constitute a threat. It says that an object displaying anomalous behavior warrants the mobilization of international resources, even if impact is not imminent. What does this tell us about what governments and space agencies actually believe about 3I Atlas? Official statements speak carefully about scientific curiosity, about the opportunity to study an interstellar object, about using the situation as a training exercise for tracking difficult targets. But actions speak louder than carefully worded press releases. You do not activate planetary defense systems for mere scientific curiosity. The history of planetary defense has been shaped by near misses and late discoveries. In 2013, a meteor exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs. No one saw it coming. The object approached from the direction of the sun, hidden in the glare until it was too late. That event galvanized international efforts to improve our detection capabilities, to ensure that we would never again be surprised by an incoming threat. Since then, Systems like Atlas have been scanning the sky continuously, cataloging asteroids, calculating trajectories, assessing risks. The International Asteroid Warning Network was created to coordinate responses to ensure that information flows quickly between observatories, space agencies, and governments. The system was designed for rocks on collision courses. It was designed for impacts we could see coming years in advance. It was not designed for something like 3I Atlas. The object's velocity alone places it beyond the threat model. It is moving on a hyperbolic trajectory, meaning it has more than enough speed to escape the sun's gravitational pull. It will pass through our solar system and return to interstellar space. There will be no impact. The mathematics are unambiguous. So why the protocol activation? The answer may lie in what planetary defense actually means, in an era when threats from space might not be limited to dumb rocks following predictable orbits. If an object displays anomalous behavior, if it maneuvers, if it shows signs of active propulsion or guidance, then the threat is not from impact, but from intent. And intent requires intelligence. Intent requires technology. Intent requires something or someone making decisions. This is the unspoken concern that hovers behind every technical briefing, every press release, every carefully neutral statement from space agencies. We have built our entire framework for understanding space around the assumption that we are alone. That assumption is the bedrock of astronomy, planetary science, and SETI. But what happens when an object arrives that behaves as if the assumption is wrong? The spacecraft intercepts offer a chance to gather data that could resolve some of these questions. When Hera and Europa Clipper fly through the tail of 3I Atlas in late October and early November, their instruments will be sampling material that was part of the nucleus mere hours or days earlier. Spectrometers will analyze elemental composition. Particle detectors will measure the size distribution of dust grains. Magnetometers will search for magnetic field signatures that could indicate metallic structures or unusual electromagnetic activity. These are not observations filtered through hundreds of millions of miles of space. This is direct contact, as close as we can get without rendezvousing with the nucleus itself. If there is something artificial about 3I Atlas, if its composition includes materials or structures that cannot be explained by natural processes, the spacecraft might detect it. But there is a dark possibility that haunts this moment. The spacecraft will gather their data and transmit it back to Earth. That transmission will take time. The data will then enter analysis pipelines, be reviewed by mission scientists, be cross-checked and validated. By the time any anomalous findings might be publicly disclosed, weeks or months could pass. And in that time, 3I Atlas will have passed perihelion, emerged from behind the sun, and either revealed its nature through its subsequent behavior, or maintained its ambiguity. This is where Avi Loeb's accusations of lack of transparency gain their weight. In an age of instant communication and social media, the slow, grinding machinery of institutional science feels like obstruction. When data exists that could answer profound questions, every day of delay feels like a choice. Every internal review process feels like gatekeeping. Whether this perception is fair or not, it shapes the narrative. Loeb has positioned himself as an outsider, challenging a complacent establishment. He argues that science has become too conservative, too wedded to conventional explanations, too afraid of ridicule to seriously consider possibilities that fall outside accepted frameworks. His advocacy for the artificial hypothesis is not presented as certainty, but as a legitimate scientific question that deserves rigorous investigation rather than dismissal. The counterargument from the mainstream scientific community is that extraordinary claims require extraordinary evidence. Proposing an artificial origin for 3I Atlas is perhaps the most extraordinary claim possible. It implies not only that intelligent life exists elsewhere, but that it has achieved interstellar travel, and that we are now observing its technology. Such a conclusion cannot be reached based on anomalies alone, no matter how striking. It requires positive evidence of artificiality, something that cannot be explained any other way. Dr. Perez-Couteau's simulations represent this more cautious approach. His team has modeled various scenarios in which natural outgassing, asymmetric jets caused by irregular heating of the nucleus, or unusual composition could produce the observed behaviors. While none of these models perfectly match all observations, they demonstrate that natural mechanisms exist that could explain at least some of what we see. This is how science is supposed to work. Competing hypotheses are tested against observations. Models are refined. More data is gathered. Gradually, explanations that fit all the evidence emerge, while those that do not are discarded. But this process takes time, and the public watches 3I Atlas with an urgency that does not align well with methodical investigation. The chemical signature remains the most troubling piece of the puzzle. Nickel and iron are forge mates. They form together in the cores of massive stars and are expelled together when those stars explode as supernovae. They condense together in the clouds of dust and gas that form new solar systems. They appear together in asteroids, in planets, in comets. The ratio varies somewhat depending on conditions, but it varies within a predictable range. 3I Atlas exists outside that range. Its nickel emissions without corresponding iron suggest either a formation environment radically different from anything we understand, or a process of refinement that separated these elements. Refinement is not a natural process. Refinement implies technology. Refinement implies purpose. Avi Loeb has compared the chemical signature to industrial alloys, materials designed for specific properties. High nickel content provides corrosion resistance and strength at elevated temperatures. These are properties you might want in a heat shield, in a propulsion system component, in any structure designed to operate in the harsh environment near a star. The comparison is speculative, but not absurd. It is based on engineering principles we understand. The alternative explanation requires that somewhere in the galaxy, perhaps around a star very different from our Sun, perhaps in a molecular cloud with unusual elemental abundances, conditions existed that could produce a comet with this composition. It requires that we expand our understanding of what is possible in natural astrophysical environments. This is not inherently problematic. Science advances by discovering that nature is stranger and more diverse than we imagined. But it does require a mechanism, a plausible process that could yield this result. So far, no such mechanism has been convincingly demonstrated. Proposals exist. Ideas are being tested. But the chemical signature of 3I Atlas remains unexplained by natural frameworks, which is why it continues to fuel speculation about artificial origins. The carbon dioxide dominance in the coma adds another dimension. The James Webb Space Telescope observations showed a composition that suggests this object formed in a cold, carbon-rich environment. Perhaps a solar system around a carbon star, where carbon compounds are more abundant than oxygen compounds. Perhaps in the outer reaches of a protoplanetary disk where water ice had been depleted but carbon dioxide remained. These environments exist in theory. Whether they produce comets with exactly the composition we see in 3I Atlas remains an open question. Every attempt to explain 3I Atlas naturally requires invoking special conditions, unusual circumstances, rare formations. Individually, each explanation might be reasonable. But when you need to invoke multiple unlikely scenarios simultaneously to explain a single object, a pattern emerges. Either we are witnessing an extraordinarily improbable natural coincidence, or we are witnessing something that is not natural. This is the epistemological razor edge on which the entire debate balances. The anti-tail phenomenon deserves deeper examination. When a comet approaches the sun, radiation pressure and the solar wind push material away from the nucleus. This creates the classic tail that always points away from the Sunday. The physics are straightforward and well understood. For material to move toward the sun requires either that it was ejected with enormous velocity from the nucleus, overcoming the outward radiation pressure, or that it is being actively propelled. Avi Loeb's interpretation of the anti-tail as a braking thrust relies on this physics. If an object were decelerating as it approached the sun, it would need to direct exhaust forward toward the Sunday. That exhaust would create exactly the visual signature observed, a stream of particles pointing sunward. The subsequent transition to a normal tail could represent the end of the deceleration burn and the resumption of passive behavior, allowing natural solar wind dynamics to dominate. Critics of this interpretation argue that irregular outgassing can create forward-directed jets. Comets are not smooth spheres. They have irregular surfaces, craters, and vents. Gas erupting from a vent on the sunward side of the nucleus could carry dust particles forward, creating the appearance of an anti-tail. This is true. Such phenomena have been observed in solar system comets. But have they been observed on the scale and with the persistence seen in 3I Atlas? The detailed timeline of the anti-tail's appearance and disappearance has not been fully disclosed in public data releases. This is one of the points of contention. Knowing exactly when the feature appeared, how long it lasted, and how it transitioned to a conventional tail would provide crucial information for modeling. If that data exists in spacecraft observations or in classified analysis, its withholding becomes significant. October 29th, 2025 approaches. Behind the sun, hidden from our view, 3I Atlas reaches perihelion. If it is a natural comet, it is experiencing maximum solar heating. Volatile materials are vaporizing at their highest rate. The nucleus, if it is made of ice and rock, may be fragmenting under thermal stress. Some comets break apart at perihelion. They come too close, and the sun's heat tears them apart. Will 3I Atlas survive its closest approach? If it is something else, if the artificial hypothesis has any validity, then perihelion represents a critical waypoint. The Oberth maneuver possibility means that any course change executed now will be maximally efficient. A small propulsive burn at perihelion can produce a large change in the final trajectory. Mission planners use this principle routinely. The Voyager spacecraft used Jupiter's gravity and well-timed burns to reach the outer solar system. Every Mars mission times its engine burns carefully to leverage orbital mechanics. If 3I Atlas emerges from solar conjunction with a trajectory that differs from predictions based on gravitational forces alone, it will be noticed immediately. Astrometry is precise. We can calculate where an object should be based on its last known position and velocity, accounting for all gravitational influences from the Sun and planets. Any deviation from that predicted position or velocity represents an external force. For a comet, that external force is usually asymmetric outgassing, the rocket effect from vaporizing ice. But the magnitude and direction of that force can be estimated based on the object's brightness and activity level. If the trajectory change is too large for the observed activity, if it occurs in a direction that cannot be explained by outgassing patterns, then we will have our answer. Not a conclusive answer, perhaps. There will still be debate. There will still be alternative explanations proposed. But it will shift the conversation fundamentally. It will move the artificial hypothesis from fringe speculation to serious consideration. The waiting period is excruciating for everyone involved. Scientists who have dedicated their careers to understanding comets and asteroids are watching their field potentially transform. SETI researchers who have spent decades listening for radio signals are confronting the possibility that first contact might come not through communication, but through direct visitation. Defense and intelligence agencies are gaming out scenarios that until recently would have been dismissed as science fiction. What do you do if an interstellar object displays clear evidence of being artificial but makes no attempt to communicate? What if it simply performs its observations or executes its mission profile and departs? Do you attempt communication? Do you attempt to intercept or rendezvous? Do you treat it as a potential threat, a scientific opportunity, or some combination of both? These questions were theoretical until July 2025. They existed in policy papers and academic discussions about protocols for first contact. Now they are being asked in secure briefing rooms and emergency planning sessions. The activation of the International Asteroid Warning Network is not just about tracking, it is about readiness. It is about ensuring that if action becomes necessary, the infrastructure and decision-making processes are already in place. But action toward what end? If 3I Atlas is artificial, it is already demonstrating capabilities far beyond anything humanity possesses. It has traveled between stars. It is operating in the inner solar system. It is maneuvering if the observations are correct. We have no spacecraft that could catch it. We have no means of communicating if it does not wish to communicate. We have no weapons that could affect it, even if we decided that was appropriate, which raises profound ethical and strategic questions we are unprepared to answer. Perhaps the activation of planetary defense protocols is not about defending against 3I Atlas itself. Perhaps it is about preparing for what comes after. If this object is a probe or scout, if it is gathering data about our solar system and our civilization, then its departure and eventual return to its origin might trigger a response. A second object, a fleet, direct contact. The scenarios multiply and branch into countless possibilities, most of them utterly beyond our ability to predict or control. This is the terror and the wonder of this moment. Humanity has spent its entire existence on a single planet, looking up at the stars and wondering. We have sent our own probes to explore our solar system and beyond. Voyager 1 and Voyager 2 are now in interstellar space, carrying messages for anyone who might find them. We have broadcast radio signals. We have listened with massive dishes. We have searched for biosignatures in the atmospheres of exoplanets. We have done everything we can to answer the question, are we alone? And now, something has arrived that might answer us. The European Space Agency's data from the Mars Orbiter flyby on October 3rd represents our closest look at 3I Atlas so far. Those instruments were not designed for this purpose. They were designed to study Mars, its atmosphere, its geology, but they are sophisticated and sensitive, and their fortuitous positioning allowed observations that Earth-based telescopes cannot match. Colin Frank Wilson confirmed the observations would be conducted. What he did not confirm, what has not been disclosed, is what those observations showed. There is data. It exists. It is being analyzed. But the findings have not been released publicly, at least not in detail. This is normal in scientific research. Data must be validated, calibrated, interpreted before publication. But normal timelines feel agonizing when the subject is potentially the most important discovery in human history. The spacecraft intercepts by Hera and Europa Clipper will add critical in situ data to our understanding. These encounters represent humanity's first direct sampling of material from an interstellar visitor while it is still active. The tail of a comet contains freshly released particles from the nucleus, material that was locked in ice for billions of years until solar heating liberated it. Chemical analysis of these particles can reveal the conditions under which they formed, the stellar environment that created them. If 3I Atlas formed around a star different from our Sun, the isotopic ratios of its elements will reflect that different nuclear furnace. Every star produces elements in slightly different proportions based on its mass, age, and composition. These isotopic fingerprints are signatures that can tell us about the object's origin. But more than that, they can tell us if the material shows signs of processing, of refinement, of manipulation that would not occur naturally. Naturally occurring materials have characteristic isotopic distributions. Industrial processing changes those distributions. Enrichment, separation, refinement all leave marks. If the particles sampled by the spacecraft show isotopic ratios that suggest processing, it would be powerful evidence for artificiality. Not conclusive on its own, perhaps, but when combined with the trajectory, the chemical composition, the anti-tail, and all the other anomalies, it would tip the scales significantly. The challenge is that this data will take time to analyze. Mass spectrometry is precise but slow. Each sample must be carefully examined. The instruments aboard Hera and Europa Clipper were not optimized for this analysis. They will do what they can with the tools they have, but these are spacecraft designed for other missions. The data will be valuable, but may not provide definitive answers. And so we return to December. Early in the month, 3I Atlas will emerge from behind the Sunday observatories around the world, will reacquire the object. The first priority will be astrometry, precisely measuring its position. Those measurements will be compared against predictions. The difference, if any, will tell us if something happened during the hidden perihelion passage. If the trajectory matches predictions within expected margins, it will support the natural hypothesis. It will suggest that whatever unusual properties 3I Atlas possesses, it is still fundamentally a passive object following the laws of orbital mechanics. The anomalies will remain unexplained, but the most dramatic possibility, active propulsion and maneuvering, will be less likely. If the trajectory shows deviations that cannot be explained by known forces, everything changes. The scientific community will mobilize. Every available instrument will focus on the object. Governments will convene emergency sessions. The media will explode with speculation, and humanity will confront the reality that we are not alone, that intelligence exists beyond Earth, and that it has reached our solar system. Avi Loeb has staked his reputation on the possibility of this second outcome. He has been vocal, persistent, and willing to endure criticism from colleagues who view his hypotheses as premature and sensationalist. But he has also been methodical. He has proposed specific tests, specific observations that could distinguish between natural and artificial origins. The perihelion trajectory change is one such test. The isotopic analysis of tail particles is another. These are falsifiable predictions, the hallmark of genuine scientific inquiry. The accusation of a NASA cover-up adds a political dimension to what should be a purely scientific question. If data is being withheld, whether for legitimate review processes or for more concerning reasons, it undermines public trust at a moment when transparency is crucial. The images from the Mars Reconnaissance Orbiter, if they exist, and show something unexpected, should be released. The scientific community and the public have a right to see what our instruments have captured. But there is a counter-argument. If those images show something that suggests artificiality, releasing them without proper analysis and context could trigger panic. Social media would spread the images globally within minutes. Interpretations, many of them incorrect, would proliferate. Conspiracy theories would flourish. The careful, methodical process of scientific validation would be overwhelmed by public reaction. This is the dilemma facing space agencies. Transparency versus responsibility. Immediate disclosure versus careful analysis. The public's right to know versus the danger of premature conclusions. There may be no right answer, only choices with different costs and benefits. The trajectory alignment with the ecliptic plane remains a nagging statistical anomaly. The ecliptic is not a physical thing. It is simply the plane defined by Earth's orbit, which happens to align closely with the orbits of most other planets because we all formed from the same rotating disk of material around the Sunday. An object entering from interstellar space could come from any direction. The sphere of possible approach vectors is vast. For 3I Atlas to arrive on a path so closely aligned with this plane is like throwing a dart at a globe and hitting a specific line of latitude. It can happen. Probability is not impossibility, but it is unexpected enough to warrant attention. Some have suggested that interstellar objects might naturally travel along the galactic plane, the flat disk of our Milky Way galaxy, and that this could bias their arrival directions. But 3I Atlas is not aligned with the galactic plane. It is aligned with our local ecliptic, a far more specific and unlikely alignment. If the object were deliberately targeting our solar system, if it were an intentional visitor rather than a random passerby, you would expect it to arrive on a trajectory that makes observation of our planets efficient. You would expect it to travel through the plane where all the interesting activity is happening, rather than diving down from above or up from below the plane. The ecliptic alignment is exactly what you would choose if you were designing an observation mission. This reasoning is speculative. It assumes intent without evidence of intent, but it is not unreasonable speculation. It is an attempt to make sense of an improbable observation by considering what that observation might mean if it is not random. The brightness variations that were cited as one reason for the planetary defense activation have not been fully explained in public briefings. All comets vary in brightness as they approach and recede from the Sunday. The amount of solar heating changes, which changes the rate of outgassing, which changes how much dust and gas surrounds the nucleus, which changes how much sunlight is reflected and scattered. These variations are predictable within certain ranges. Unexpected variations mean changes that do not match the model. They mean brightness fluctuations that occur too rapidly or too slowly, that are too large or too small, that happen at times when they should not happen. Such variations could indicate that the nucleus is fragmenting, that large pieces are breaking off. They could indicate that outgassing is highly asymmetric and variable. Or they could indicate changes in the object's orientation, its tumbling rate, or its configuration. If 3I Atlas is artificial, if it has deployable components or adjustable surfaces, then brightness variations could reflect operational changes. Imagine a spacecraft deploying solar panels or extending instruments. Imagine a probe adjusting its orientation to point sensors at targets of interest. These actions would change the cross-section presented to sunlight, changing the brightness as seen from Earth. Again, this is speculation, but it is grounded in engineering principles. The waiting continues. November passes. The Planetary Defense Protocol runs its course, training personnel, refining procedures, ensuring that international coordination functions smoothly. It is all described as an exercise, a learning opportunity. But exercises are most valuable when they prepare you for real scenarios. What real scenario does tracking a non-threatening interstellar object prepare us for? The answer is obvious once you think about it. It prepares us for tracking threatening interstellar objects. It prepares us for a situation where something arrives that we do not understand, that behaves unpredictably, that might require rapid assessment and response. It prepares us for the possibility that 3I Atlas is not unique, that it might be the first of many, and that the next visitor might not be so benign. December arrives. Observatories prepare. The first opportunities to reacquire 3I Atlas come in the pre-dawn hours. Telescopes in the southern hemisphere have the best viewing angles initially. Then, as the object's position shifts relative to Earth and Sun, northern observatories join the campaign. Everyone is watching. Professional astronomers, amateur observers, space agencies, governments, the media, the public. The first position measurements come in. They are compared against predictions. Teams run calculations. Orbital determination software processes the data. Within hours, preliminary orbits are computed. Within days, those orbits are refined. The question everyone is asking is simple. Did it change course? The data will speak. Numbers do not lie, though their interpretation can be contested. If the orbit matches predictions, the debate will continue, but the artificial hypothesis will be weakened. If the orbit shows deviations, the debate will intensify dramatically. But regardless of what the December observations show, 3I Atlas has already changed something fundamental. It has forced humanity to confront possibilities we were content to leave theoretical. It has activated systems designed to protect us from threats we thought we understood. It has divided the scientific community between those who counsel caution and those who advocate for bold new hypotheses. It has made millions of people look up at the night sky with a new awareness that we may not be alone. The SETI community has spent decades searching for radio signals from distant civilizations. The assumption has always been that first contact would come through electromagnetic communication, deliberate messages sent and received across the light years. The equipment has been built, the search strategies have been refined, thousands of stars have been examined. But what if first contact comes differently? What if advanced civilizations do not broadcast their presence but instead send probes, small, automated spacecraft that can travel between stars over centuries or millennia, gathering data and reporting back? What if the galaxy is crossed not by radio waves, but by physical emissaries, silent observers that arrive, perform their missions, and depart? This is a legitimate strategy for exploration. We have done it ourselves on a small scale. The Voyager spacecraft carry messages for potential finders. We have sent probes to every planet in our solar system. If we had the technology for interstellar travel, sending automated probes to nearby star systems would be a logical next step. Why assume that other civilizations would not follow the same logic? If 3I Atlas is such a probe, it represents a profound shift in how we think about the search for extraterrestrial intelligence. It means that rather than listening, we should be watching. Rather than pointing radio telescopes at distant stars, we should be monitoring our own neighborhood for visitors. It means that contact might already be happening, quietly and without fanfare, as automated systems gather data about us and our planet. The implications cascade outward. If there are probes in our solar system, how many? Are they watching us continuously? Have they been here for years, decades, centuries? Do they communicate with each other? Do they communicate back to their origin? Are we being observed, studied, cataloged by intelligences we cannot detect because we do not know what to look for? These questions were the domain of speculation and science fiction. 3. I-ATLAS has dragged them into the realm of serious scientific consideration. Even if this particular object turns out to be natural, even if every anomaly eventually receives a conventional explanation, the possibility has been raised. The door has been opened. We cannot unlearn what we now know might be true. The philosophical implications are staggering. Every human civilization has developed stories about its place in the cosmos. We have imagined gods and spirits. We have wondered about other worlds. In the modern era, we have searched systematically for evidence of life beyond Earth, but always with the comfortable distance of billions of miles between us and any answer we might find. 3. I-ATLAS is here. It is in our solar system, passing through our neighborhood, close enough to study with our instruments. If it is artificial, if it represents technology from another civilization, then the abstract question of extraterrestrial intelligence becomes immediately, viscerally concrete. We are not alone. We have never been alone. And we have been observed. The psychological impact of such a revelation would be immense. Every religion would need to grapple with how this fits into their understanding of creation and humanity's significance. Every government would need to consider the implications for security, for sovereignty, for international cooperation. Every individual would need to reconcile their sense of human uniqueness with the reality of being one intelligence among many. But perhaps we are getting ahead of ourselves. Perhaps 3I-ATLAS is natural. Perhaps every anomaly will eventually be explained by cometary science we have yet to fully develop. Perhaps the trajectory alignment is just extraordinary luck. Perhaps the chemical signature reflects formation conditions we simply do not yet understand. Perhaps the anti-tail was a temporary outgassing jet. Perhaps all of this has a conventional explanation that will satisfy Occam's razor once we have sufficient data. This is certainly possible. Science is full of examples where seemingly impossible observations turned out to have prosaic explanations. Strange signals that seemed like alien communication turned out to be pulsars. Unusual chemical signatures that seemed biological turned out to be geological. The history of science teaches humility in the face of the unknown, but it also teaches us to follow the evidence wherever it leads. If the evidence points towards something extraordinary, we cannot dismiss it simply because it challenges our assumptions. We must investigate rigorously, test thoroughly, and be willing to accept conclusions that revolutionize our understanding. This is where we stand as December unfolds. The observations are being made. The data is being analyzed. Avi Loeb and his supporters are watching for signs of trajectory change. Mainstream scientists are running models and searching for natural explanations. Space agencies are coordinating observations and managing information flow. Governments are quietly gaming out scenarios and updating contingency plans. And 3I-ATLAS continues its journey, oblivious or aware, natural or artificial, random or intentional. It is moving away from the sun now, headed back toward the outer solar system and eventually to interstellar space. Every day it grows dimmer as the distance increases. Every day it becomes harder to observe. By mid-2026, it will be too faint for all but the largest telescopes. By 2027, it will be lost to our instruments, disappearing back into the cosmic darkness from which it emerged. We have a limited window to extract every possible piece of information from this visitor. The observations being made now may be all we ever get. There will be no second chance. If we miss crucial data, if we fail to ask the right questions or point the right instruments, the answers will leave with the object. This urgency drives the intensity of current efforts. Every observatory with relevant capabilities is involved. Amateur astronomers are contributing observations. Space agencies are coordinating unprecedented collaborations. The scientific community has mobilized in a way rarely seen outside of major anticipated events like solar eclipses or asteroid flybys. But beyond the scientific questions lies something more profound. 3. IATLAS has reminded us that we are part of a galaxy containing hundreds of billions of stars, many of them with planets. Some of those planets potentially harboring life. We are not isolated. We are not the only story being written in the cosmos. Whether this particular object is natural or artificial, whether we are being visited now or still waiting for first contact, the possibility is real. The universe is vast beyond comprehension. The Milky Way alone contains more stars than there are grains of sand on all the beaches of Earth. Around those stars orbit planets in unimaginable diversity. And among those planets, the laws of chemistry and biology that led to life on Earth almost certainly operate elsewhere. Intelligence might be rare. Technology might be rarer still. But in a galaxy this large, with this many opportunities, the odds approach certainty. We are not special. We are not unique. We are one outcome of cosmic evolution, one experiment in self-awareness and tool-building among countless others. This realization is both humbling and exhilarating. It places our petty conflicts and divisions in cosmic perspective. What does any human disagreement matter when measured against the possibility that we are about to confirm we are not alone? The December observations will tell us something important about 3 IATLAS. They may not give us all the answers. They may raise more questions than they resolve, but they will move us forward. They will refine our understanding. They will either support the natural hypothesis and send researchers back to develop better models of exotic comets, or they will support the artificial hypothesis and change everything. Either outcome advances knowledge. Either outcome is valuable. But one outcome is routine, an addition to cometary science, while the other is revolutionary, the most significant discovery in human history. The asymmetry is profound. What would you do if you were in charge of analyzing this data? Would you rush to publish findings that might be wrong but sensational? Would you hold back conclusions, waiting for certainty that might never come? Would you err on the side of caution or boldness? These are not easy choices. They require balancing scientific integrity with responsibility to the public, institutional reputation with historical significance. The scientists analyzing 3 IATLAS are living through a moment they will remember forever, regardless of what they find. They are the first humans to have the opportunity to potentially confirm that we are not alone. That burden of responsibility must be immense. Every decision they make, every interpretation they choose, every delay or acceleration in publication has consequences that ripple across all of humanity. We should acknowledge their dedication. Most of them work long hours for modest pay, driven by curiosity and passion rather than financial reward. They have trained for years, decades, to develop the expertise needed to extract meaning from faint signals and subtle variations. They are doing their best to answer questions that previous generations could only dream about asking. But we should also demand transparency. The data being gathered with public funding, with instruments built by international cooperation, belongs to humanity. It should be shared as fully and rapidly as possible, consistent with scientific validity. The balance between careful analysis and timely disclosure must lean toward openness, especially for a subject this important. As the observations continue and data accumulates, a picture will emerge. It may be a picture of an unusual but natural comet from an exotic stellar environment. It may be a picture of something we have no framework for understanding, something that forces us to expand our conception of what is possible. We will adapt either way. Humans are remarkably good at incorporating new information into our worldviews. But the waiting is hard. November felt eternal. December will feel longer. The hours between observation sessions stretch. The time lag between data collection and publication feels interminable. Everyone involved, from professional astronomers to interested members of the public, shares a common desire. Tell us what you are finding. The story of 3I Atlas will continue to unfold over the coming weeks and months. This is not a story with a single climactic revelation. It is a slow accumulation of evidence, a gradual convergence toward understanding. Each new data point adds a piece to the puzzle. Each new analysis refines the picture. But some moments matter more than others. The December reacquisition matters. The trajectory measurements matter. The spacecraft tail intercept data matters. The spectroscopic analysis of composition matters. These are the critical pieces that will shape the narrative. And somewhere in all of this data, hidden in the numbers and graphs and spectral lines, lies the answer to whether humanity is experiencing its first encounter with technology from beyond Earth, or whether we are witnessing an extraordinary but natural cosmic phenomenon that will expand our understanding of how planets and comets form around other stars. The truth is there. We simply need to extract it from the observations, interpret it correctly, and have the courage to accept it, regardless of how it challenges our preconceptions. 3I Atlas will leave. It will continue on its hyperbolic trajectory back into interstellar space. In a few years, it will be beyond the orbit of Neptune, racing toward the heliopause and the boundary of our solar system. In a few decades, it will be light years away, forever beyond our reach. But it will leave something behind. It will leave questions answered or unanswered. It will leave humanity changed, having glimpsed possibilities we cannot forget. It will leave a legacy in our science, our philosophy, our understanding of our place in the universe. This is the gift and the burden of 3I Atlas. It arrived from between the stars and demanded that we confront what that might mean. It forced us to look up and wonder not just about distant galaxies and ancient light, but about visitors that might be passing through our neighborhood right now. The cosmos is not empty. The space between stars is not void. Objects travel those vast distances. Some are random, flung out by gravitational interactions. Some might be intentional, sent by civilizations we have yet to meet. We have learned to detect these visitors. We have built the instruments and the systems to track them. Now we must learn what to do with what we find. 3I Atlas is teaching us. Whether its lessons are about exotic cometary chemistry or about the technology of other civilizations, we will be changed by learning them. We will see the night sky differently. We will plan our future in space differently. We will think about our significance differently. The object that arrived on July 1st, that triggered planetary defense protocols in September, that hid behind the sun in October, and that will emerge in December, has already accomplished something profound. It has reminded us that we live in a universe full of mysteries, some of which might come to us rather than waiting for us to travel to them. And in that reminder lies the most important lesson. We must remain alert. We must remain curious. We must continue building better instruments and training better observers. Because 3I Atlas may not be the last interstellar visitor. It may not even be the most interesting one. The future is opening before us, full of possibilities we are only beginning to imagine. What we learn from 3I Atlas will prepare us for what comes next. And something will come next. The universe is too vast, too active, too full of wonders for this to be the end of the story. it is only the beginning. The December sky holds secrets that will reshape our understanding of reality itself. As telescopes around the world prepare to reacquire 3I Atlas, as teams of astronomers ready their instruments and analysis software, as governments brief their leadership on possible outcomes, we must ask ourselves, are we ready for the answer? The question is not merely scientific, it is existential. If 3I Atlas proves to be natural, we will have learned something valuable about cometary diversity and the variety of planetary systems that exist around other stars. We will update our models. We will expand our textbooks. Science will advance incrementally, as it usually does. But if the object proves to be artificial, if the trajectory shows evidence of propulsion, if the chemical signatures definitively point toward manufactured materials, then we face a transformation far more profound than any scientific discovery in human history. Consider what it would mean. Not a radio signal from hundreds or thousands of light years away, not a theoretical possibility discussed in academic papers, but physical evidence of extraterrestrial technology operating in our solar system right now. It would confirm that intelligent life exists elsewhere. It would confirm that interstellar travel is possible. It would confirm that we are being observed, studied, perhaps even evaluated by minds and motives we cannot fathom. The immediate questions would multiply faster than we could answer them. Who built it? When was it launched? How does it work? What is its mission? Is it autonomous or remotely controlled? Does it pose any threat? Can we communicate with it? Should we attempt to? The protocols developed for first contact through radio signals would be inadequate for a physical visitor already in our midst. International cooperation would become essential overnight. The United Nations would need to coordinate responses. Space agencies would need to share data fully and immediately. Military and civilian authorities would need to establish clear chains of command and decision-making processes. The planetary defense protocols activated for 3I Atlas would transition from training exercise to operational reality. But beneath these practical concerns lies something deeper. The knowledge that we are not alone would fundamentally alter human consciousness. Every person on Earth would need to integrate this reality into their understanding of existence. We are one species among many. Our technology, our civilization, our history are not unique. Somewhere out there, other beings followed their own path, from primitive origins to spacefaring capability. They built their own societies, developed their own science, and eventually reached out into the cosmos. This realization would be humbling and inspiring in equal measure. Humbling because it demonstrates that humanity is not the pinnacle of creation, not the inevitable endpoint of cosmic evolution. Inspiring because it proves that intelligence can arise, survive, and flourish, that civilizations can persist long enough to achieve interstellar capabilities, that the universe is not a sterile wasteland, but a garden in which many flowers bloom. The religious implications would be immediate and profound. Every faith tradition would need to grapple with how extraterrestrial intelligence fits into their cosmology. Some would find accommodation easily, interpreting revelation through a broader lens that includes other worlds and other beings. Others would face more challenging theological questions about creation, salvation, and humanity's relationship with the divine. But most would ultimately adapt, as religions have always adapted when confronted with new knowledge about the nature of reality. The secular world would face its own reckoning. Our economics, our politics, our social structures are all built on assumptions of human centrality and isolation. We compete for resources as if they are scarce, and we are alone in claiming them. We fight wars over territory as if our planet is all that exists. We pursue narrow national interests, as if global cooperation is optional. The arrival of an interstellar visitor would expose the pettiness of these conflicts and the urgency of presenting a united human front to whatever lies beyond. Education systems worldwide would need to be updated immediately. Children would grow up knowing with certainty that humanity shares the universe with other intelligences. The psychological impact of this knowledge on developing minds would be significant. How would it shape their ambitions, their fears, their sense of possibility? Would they feel more connected to the cosmos or more vulnerable within it? The scientific community would face its greatest challenge and opportunity. Entire new fields would need to be developed overnight. Astroengineering, xenoarchaeology, comparative intelligence studies. Researchers would need to develop frameworks for understanding technology and thought processes that might be radically different from our own. The assumption that we can understand alien artifacts through our own physics and mathematics might prove naive. We might need fundamentally new approaches. But let us not get too far ahead. Let us return to what we know and what we will soon discover. 3. I-Atlas is emerging from solar conjunction. The first observations are being made. Position measurements are being compared against predictions. The critical question hangs in the balance. Did it maneuver? If it did not, if the orbit matches gravitational predictions within expected margins, the debate will shift, but not end. The chemical anomalies will still demand explanation. The trajectory alignment will still seem improbable. The antitail will still lack a fully satisfactory natural mechanism. Avi Loeb and others will argue that absence of observed maneuvering is not proof of absence of capability. Perhaps the object did not need to adjust its course. Perhaps it was already on the trajectory it intended. Perhaps observation is passive and requires no active propulsion. The skeptics will point to the orbital match as powerful evidence for natural origin. If it were artificial, they will argue, why would it not maneuver? Why follow a purely ballistic path? Why not demonstrate capability or alter course for better observation angles? The absence of maneuvering would be a significant blow to the artificial hypothesis, though not necessarily a fatal one. But if the orbit does not match predictions, if there is a deviation that cannot be explained by outgassing or gravitational perturbations, then we enter uncharted territory. The magnitude of the deviation will matter. A small change might still be attributed to asymmetric cometary jets. A large change, particularly if it occurs in a direction that serves an obvious purpose like course correction or velocity adjustment, would be much harder to explain naturally. The direction will matter as much as the magnitude. A random deviation could be natural. A deviation that aligns with efficient trajectory modification, that demonstrates understanding of orbital mechanics, that serves an apparent purpose, would strongly suggest intentional action. Mission planners would recognize the signature of a designed maneuver. The pattern would be familiar because we use the same principles when navigating spacecraft through the solar system. Avi Loeb has been explicit about what he expects to see if 3I-Atlas is artificial. He has laid out testable predictions. This is proper scientific methodology. The predictions can be checked against observations. If they match, the hypothesis is strengthened. If they do not, the hypothesis must be revised or abandoned. This is how science works at its best, through bold proposals subjected to rigorous testing. His critics argue that he has been premature, that he has advocated for extraordinary conclusions before sufficient evidence has been gathered. They worry about the damage to scientific credibility if prominent researchers promote speculative ideas that turn out to be wrong. They fear that public trust in science, already fragile, will be further eroded by high-profile failures to deliver on dramatic predictions. These concerns are valid, but they must be balanced against the risk of excessive caution. Science advances through bold hypotheses that challenge consensus. Plate tectonics was ridiculed before it was accepted. The Big Bang was controversial before it became standard cosmology. Exoplanets were barely taken seriously before we found thousands of them. Every major scientific revolution began with someone willing to propose ideas that seemed outlandish to their contemporaries. The question is not whether Avi Loeb might be wrong. He might be. The question is whether his hypothesis is worth investigating rigorously, whether it makes testable predictions, whether it could possibly be right. On all these criteria, the artificial origin hypothesis qualifies as legitimate science, regardless of how uncomfortable it makes the establishment, and discomfort is understandable. Accepting the possibility that 3I Atlas might be artificial requires accepting that everything might change. It requires preparing for a future radically different from the past. It requires admitting that our understanding of our place in the cosmos might be fundamentally incomplete. These are not easy things for individuals or institutions to embrace. But reality does not care about our comfort. The universe is what it is, regardless of our preferences. Our responsibility as a species is to seek truth courageously, to follow evidence fearlessly, to accept conclusions honestly even when they terrify us. This is the essence of intellectual integrity. This is what separates science from dogma. The data from the spacecraft tail intercepts will add another crucial piece to the puzzle. When those results are published, when we see the detailed compositional analysis of particles sampled directly from the coma of 3I Atlas, we will know more. If the isotopic ratios are consistent with natural astrophysical processes, it will support the natural hypothesis. If they show signs of refinement or processing, it will support the artificial hypothesis. The challenge is distinguishing between unusual natural compositions and truly impossible ones. Every element has multiple isotopes, different versions with the same number of protons, but different numbers of neutrons. Natural processes produce characteristic ratios of these isotopes, but those ratios can vary based on the details of where and how the material formed. Interpreting isotopic data requires careful modeling and comparison with known reference samples. If the particles show isotopic signatures that match no known natural environment, that cannot be produced by any plausible astrophysical process, that look instead like the products of industrial separation or enrichment, we will have our answer. This kind of evidence would be unambiguous. It would not require elaborate interpretation or statistical arguments. It would simply be data that cannot be natural, that must be artificial. The scientific publications that will emerge from 3I Atlas will be studied for generations. Regardless of whether they conclude natural or artificial origin, they will represent humanity's most detailed examination of an interstellar visitor. They will establish protocols for future observations. They will identify what kinds of data are most valuable. They will highlight what instruments and techniques work best. All of this will prepare us for the next visitor, because there will be a next visitor. 3. I-Atlas is the third confirmed interstellar object. 1. I-Oumuamua arrived in 2017, sparking its own controversy over possible artificial origins. 2. I-Borisov followed in 2019, a more conventional comet that fit expectations. Now, 3. I-Atlas has arrived with its cascade of anomalies. The detection rate is increasing as our survey systems improve. We will see more of these objects in coming years and decades. Each one will be an opportunity for discovery. Each one will tell us something about the diversity of planetary systems and the processes that eject material into interstellar space. Each one might, just possibly, be the visitor that definitively answers whether we are alone. We must be ready. We must have instruments prepared. We must have analysis protocols established. We must have international cooperation functioning smoothly. The legacy of 3I Atlas will be this preparation. Even if this particular object turns out to be natural, it has forced us to develop the capabilities and frameworks we will need when something unambiguously artificial does arrive. It has been a test, a rehearsal, a forcing function that has accelerated our readiness. The planetary defense protocols, the rapid coordination between agencies, the public communication strategies, all of these will be refined and improved because of this experience. And somewhere, in a database or a report not yet made public, may lie the answer we are seeking. The images from the Mars Reconnaissance Orbiter, if they captured 3I Atlas in enough detail, might show surface features, structure, geometry. Natural comets are irregular, lumpy, battered by impacts and shaped by outgassing. Artificial objects have different characteristics, symmetries, regularities that natural processes rarely produce. If those images exist and show an irregular ice and rock body with all the characteristics of a natural comet, the artificial hypothesis will be severely weakened. If they show something else, something with structures that appear designed, with geometries that seem intentional, with features that cannot be explained as natural formations, then everything changes, and the images must be released immediately. The longer they are withheld, the more conspiracy theories will flourish, the more public trust will erode. Transparency is not just an ethical imperative. It is a practical necessity. In an age of global communication, secrets do not stay secret for long. Leaks happen. Whistleblowers emerge. Information finds its way out. Attempting to control or suppress data about 3I Atlas would be futile and counterproductive. Better to release information openly, provide context and analysis, engage the public as partners in discovery, rather than treating them as subjects to be managed. The story of 3I Atlas, whatever its final chapter reveals, will be remembered as a turning point. It is the moment when humanity collectively confronted the possibility of contact, when we activated systems designed to protect us from the unknown, when we demonstrated that we can coordinate globally in response to a cosmic mystery. These capabilities will serve us well in the future. Regardless of what we conclude about this particular object, we are learning to be a spacefaring civilization. We are taking the first stumbling steps toward becoming active participants in the cosmic community rather than isolated observers. We are developing the technology, the institutions, and the mindset required to engage with a universe far stranger and more populous than we imagined. This is our adolescence as a species, awkward and uncertain but necessary for maturation. The children born today will grow up in a world shaped by what we learn from 3I Atlas. They will inherit either the knowledge that we are alone in a vast cosmos, making our civilization infinitely precious and our survival paramount, or the knowledge that we share the universe with others, making cooperation and wisdom essential for our place in the galactic community. Either legacy is profound. As observers turn their instruments toward the emerging object, as data begins to flow back to Earth, as preliminary orbits are computed and refined, we stand at a threshold. Behind us lies the comfort of isolation, the certainty that we are alone, the simple universe of a single intelligence on a single world. Ahead lies uncertainty, possibility, terror, and wonder in equal measure. We cannot go back. The question has been asked. The observations have been made. The anomalies have been detected. We must move forward into whatever future these discoveries reveal. And we must do so together, as a species united by the magnitude of what we face. The cosmos has sent us a visitor. Whether it is a chunk of ice and rock from an alien star system or something far more significant, it demands our attention and our best efforts at understanding. We owe it to ourselves, to future generations, to the memory of all who wondered and dreamed about other worlds, to answer the questions 3I Atlas has raised. The December observations continue. Data accumulates, analysis proceeds, and slowly, carefully, rigorously, the truth emerges from the noise. We will know soon. The waiting, agonizing as it has been, is almost over. The answer lies in the numbers, in the spectra, in the trajectories. It lies in the dedicated work of scientists around the world who have turned their careers toward understanding this visitor. Whatever they find, whatever they conclude, we will adapt. Humanity has always adapted. We learned that Earth is not the center of the universe. We learned that our sun is one star among billions. We learned that planets are common, and some might harbor life. Each revelation expanded our perspective and forced us to grow. This will be no different, only more dramatic, more immediate, more consequential. The universe is vast and old and strange. It has produced us, improbable assemblages of matter that can think and wonder and reach beyond ourselves. If it has produced us, it has surely produced others. The question has always been not whether we are alone, but when we would find out. Perhaps that moment is now. Perhaps 3I Atlas is the messenger that carries the answer. Perhaps when it emerges from behind the sun and reveals its secrets, we will finally know. And in that knowing, in that moment of confirmation or continued uncertainty, we will take another step forward as a species. We will be changed. We will be challenged. We will be compelled to rise to a level of wisdom and maturity we have not yet achieved. This is the gift of 3I Atlas. Regardless of what it ultimately proves to be, it forces us to grow. It forces us to prepare. It forces us to become worthy of the cosmos we inhabit. The telescopes are watching. The instruments are recording. The scientists are analyzing, and all of humanity, whether they know it or not, is waiting for an answer that will echo through history. This is our moment. This is when we learn whether the universe is empty or full, whether we journey alone or in company, whether our future is isolation or contact. 3I Atlas holds the answer. Soon, very soon, we will know. And whatever we learn will change everything. Thank you for being with us. Please subscribe and leave a like.